So this is NVMe over Fabrics recovering from a loss of communication. And I just want to start out by saying what my goal is here is to communicate to you what some of the things we've done in the spec group in order to make it possible to recover from a loss of communication. That I want to communicate that to you so that you can go out and in the implementations that you interact with NVMe, that you can make sure that, or implement yourself, that they do these techniques to handle this. And I'm going to go over why. We have some serious problems that we are trying to solve with the specification. And I do believe that NVMe over Fabrics is the right protocol to move forward in enterprise storage. And I want to see an increase of adoption, and I do think that this is something that is missing and needs to be incorporated in the implementations that are out there. Okay, so today we're going to talk about some of the examples of the problems we're trying to prevent. We're going to go into time-based recovery, which is what is currently published in the specification right now, including the concepts of CATO and CQT. Then we're going to talk about making it faster, because no one's happy with using this for recovery. It just takes too long. And so we'll talk about what it means to reconnect, what's coming in the specification so that we can detect a loss of host communication and can communicate that back to the host, and how to do a cross-controller reset. We are not going to cover PCIe communication loss because there are other ways of solving that problem. I won't say it's a solved problem, but there are other ways of solving that problem, and they just have a different set of issues. So we're going to focus exclusively on Fabrics here. So just to make sure that we've got common terminology here, I'm going to be referring to these terms as we go through. I'm just putting it up there. I'm not going to step through and explain them because I'm expecting that you're already familiar with them, and I don't want to put you to sleep. So some of the problems that we are trying to prevent. This is called the ghost write problem, a write that shows up after a write. And it starts out with the host sending a write to a specific address. It wants to have certain content. X in this case. And that shows up at the controller and it starts to execute it. And for some reason that it takes a long time for that controller to execute. And in the course of that time, the host detects a loss of communication. And that's not surprising. Whatever's making the controller take a long time to execute is probably getting in the way of the conversation between the two. And so the host decides to turn around and say, let's send that command over to this other controller that I'm talking to, this other path that I have available to me. And that one executes just fine really quickly, and it gets back. And so I am done writing X at that address. I can move on to the next dependent write, and I can write the next value. And I get back, and I think everything's going just fine. However, controller 1 has continued to execute that command and then finally gets around to writing X to stable storage. And at this point, at the end of the story, the LBA contains X, not Y, which is what the host thought was the last write. And if the host had waited on that retransmission of that command until down here, and before it did the retransmission, then everything would have been fine. We would have not had any problems at all. And so with time-based recovery, we're specifically trying to solve this problem. Now, there are still other problems that can happen with a loss of communication, even if you do wait. And so if the host launches a different command, let's say a namespace management command where they're creating a namespace, and controller 1 is executing it, but the host detects a loss of communication, the host doesn't know what happened with that command. And the command takes effect, a namespace is created. As far as controller 1's concerned, everything happened just fine. The host says, well, I'm going to wait because I'm a well-behaved host, And it waits until it knows that controller 1 is done with that command through some parameters we're going to talk about that are agreed on beforehand. And then it retries the command and it gets success back, and it's happy also, because it knows that this command succeeded. The problem is that on the storage, we have 2 namespaces that are created. Now, going back to the first example that I shared, so that's one example. Problem that we're dealing with here is this namespace management command, the create, is a non-idempotent command. If you issue it over and over again, you're not going to end up with the same result. You're going to have the problem is the command's going to execute and you're going to get cumulative results. So even with the beginning command with a write, even though a write is an idempotent command, you can still run into problems if there are other hosts involved. And so in this case, the host issues the write of a value to location X. The command takes effect, the host detects a loss of communication, and it waits the amount of time that it's supposed to. Well, while it's waiting, we have this other host that is following the protocol of this application that it's reading. It's the reason why this host did a write of A to this location X is because they're going through some sort of process. They're keeping track of what steps they're at in the process. And this host reads the location and says, okay, we're at step A. I can move on to step B. And I'm going to finish step B, and I'm going to write that we're at step B. Well, this other host over here didn't know that that was going on. And so when it was done waiting for that command to stop executing on controller 1, it says, okay, I've got another path. I've got a command to issue that I want to find out what happens with it. And so I issue the write, which is an idempotent command. And I get back success, and I'm like, okay, this is great, but we no longer think we got to step B in the distributed process. And so we still have a problem. Even though this was an idempotent command that we're dealing with, because there are multiple hosts involved, this wasn't the right tool to use. And one of the key points here is that the host driver doesn't know this. The host driver doesn't know that there's another host out there that's working in the upper layer application. And so the host driver cannot by itself decide whether it just needs to retry the request. That's something that the application needs to let it know if it can do that. So to understand this, to get a framework around this on how we're going to recover from these commands, we've introduced some categories. This is just a way of thinking about it. We determine the terms, but this is just trying to describe something, a concept that's already out there. That the first kind of command is idempotent and it doesn't change the state on the box. Well, maybe it keeps track, they're keeping track of stats, maybe there's a flow control thing that's going on. We're not going to worry about that. When you issue an NVM read, you're expecting that stable storage is not going to change. And so that would be considered an unrestricted retry. You can reissue these immediately. If you've got a path down, if the other guy's taken too long, you can issue the command again. With a delayed retry, if you don't get the response back from because of a loss of communication, as long as you know that the command's not executing anymore in the subsystem, you should be able to reissue that command again. You just need to wait long enough to make sure that it's okay. And so NVM write would be a good example of that, as long as there's not any other hosts that are around that are interfering with that. A state-dependent retry, that really depends, in order to know if you can issue that command again, you need to know what happened. You need to figure out you can't just get over the loss of communication, wait for the command to stop executing. You also need to know if that command actually got to the storage. And these are things that we're not expecting a driver to be able to recover from by itself. The application really needs to decide what's going on there. Some examples of these, we use namespace management command. Another example is that, well, in that two hosts going on, instead of using a write, we could have used a compare and write. Compare and write would have been a better tool to use, but we would have to deal with the fact that, well, we might get an error back on that compare and write. And so we still need to have the upper layer application involved in deciding what to do. Okay, so how do we figure out how long the command is going to be in the system? That's really what time-based recovery is about. And when we're figuring this out, we want to know how long we have to wait before we can start actually recovering from it. And so there's two parts of that. The first of it is okay, the host has detected a loss of communication. That's not necessarily when the controller detects a loss of communication. And so I think I may be using up your battery. I'm sorry. So with the loss of communication, the controller needs to detect it. The keep alive timeout is a tool that was introduced that says, okay, if I don't hear anything from the host in this amount of time, I'm assuming that the host is not talking to me anymore. And really what it does is it sets an upper bound for when the controller can say, yes, this is a loss of communication. We do have some other events, like if you got a cable pull. Well, that's not really a symmetric event. If the cable pull happens on the controller side, yeah, it detects it right away. But if it happens on the host side, the host detects it right away, but the controller may not have any idea that that cable pull happened. Now, in the instance of fiber channel tends to propagate some of these events through the network. And so if you get a cable pull in fiber channel on one side, you can generally assume that the other side knows about it because the fabric controller will let them know. And so that's the first thing, is how long does it take to know that the controller has detected a loss of communication? And the second step is how long does it take for the controller to stop processing commands? And so that's where we introduced into the specification command queue time, or command quiesce time. And that's a contract that the controller sets with the host that says that, well, if I stop talking to you, this is how long I need before I'm ready to say, yeah, I've got all of these commands cleaned up. And so this handles the case when, okay, that command was sticking around and I really didn't clean it up all that quickly. Oftentimes this is considered the failover time for an array system. And so in order to figure out when the host can recover, you really need to add up both of these times. It's not enough for the controller just to determine that there was a loss of communication. It also needs to stop processing the commands. So KTOE, command-based KTOE, or command-based keep alive, how does that operate? Basically, you're issuing a keep alive command. The host is issuing that at regular intervals. The controller is expecting it at regular intervals. If it ever doesn't see it at the intervals that the controller is expecting, then it says, okay, I don't have communication. There are some drawbacks to this. It only uses the admin queue, which is good for isolation. You're only ever talking to one queue. But that does mean that you can have a pretty healthy series of I/O commands going on between the device. And we have seen some implementations out there that don't give appropriate priority to the keep alive command. And so we've seen that the controller says that there's a KTOE because it didn't get the keep alive command even though there was a bunch of other traffic going on. It's very predictable. If you don't detect if the controller doesn't detect it doesn't receive a keep alive command, then you know exactly how long it's going to take before it spits up. The thing to remember, though, is that that keep alive command can get delayed in the network. And so to be conservative, we say that you should expect that it could get delayed 1 keep alive timeout time, because that's the amount of time that you could have a packets delayed in the network and still have a healthy connection. So in order to know that the controller has detected a keep alive timeout, you really have to wait the time that the packet was delayed in the network, and then 1 keep alive time after that. Keep alive timeout time. And so it's 2 times cap. For traffic-based keep alive, it still keeps the algorithm that if a keep alive command shows up, we restart the time. Or you can restart the time. But the key about here is that if it is receiving other traffic on other queues, it will still consider that there's a healthy communication there. And that means that you do have to have communication between cores and between the queues about that there is traffic that's going on. But it's viewed that that's worth it, because then you don't have to rely on what priority the host is giving to the keep alive commands. Now, the tricky part about it is, well, okay, how long does it take to detect a keep alive timeout then? You would think maybe it's 2 times cap, and the answer is no. That would be wrong. So this continues the assumption that you can delay a keep alive command in the network for at least 1 keep alive timer time. This also conservatively assumes that the command shows up arbitrarily close to when the last time the controller checked to see if there was a command that arrived. And so the next time that it checks, it's going to say, oh, well, I received a command, so I'm good for this entire interval. And it's not until the time after that that it actually detects a keep alive timeout. And so in order for you to be sure that the controller has detected a keep alive timeout time, you really have to go for 3 times cap. So with command-based keep alive, it was 2 times cap. With traffic-based keep alive, it's 3 times cap. Now, what does the host do in order to keep the controller alive? It's free to implement whatever algorithm that it wants. The specification is for what the controller is doing. And the controller is the one that picks between the command-based keep alive and the traffic-based keep alive. So you want the algorithm, whatever the host to do, to be roughly similar for both of them, because the host doesn't get to pick. The host also doesn't know exactly when the controller receives a command, so you have to be conservative in your estimates on when those happen. And so that translates into, when do you restart the time? When do you send the keep alive commands? You need to send the keep alive commands more frequently than the controller is expecting to receive them, because you need to be aware of delays that can commonly happen in the network. So the suggested interval for sending the keep alive commands is half a cap. So there is a more detailed example in the spec, and it takes all of these considerations into account. So with traffic-based keep alive, the host has an opportunity to not send a keep alive. And if it wants to do that, that's fine. If it doesn't, that's fine too. Everything will work just perfectly if the host decides, I'm going to do exactly the same thing, no matter whether the controller is using traffic-based keep alive or command-based keep alive. But if it decides that it doesn't want to send a packet, it should check to see if it should send a packet at 1/4 time cat instead of 1/2 time cat. And the reason is because it will send the command and it will get a response arbitrarily close to the first check. And then the next check, it will skip sending a keep alive command because it had already sent a command. So the next check that it will actually send the command is the second one. And so if you replace the 1/4 cats here with 1/2 cats, then you're going to be sending a keep alive command every cat time instead of every half cat. And the host is not going to, the controller is not going to stay alive with that. And so when you're using traffic-based keep alive, if you want to avoid sending a keep alive command, you do need to check more frequently. And if the command is idle, if the connection is idle, you will end up sending as many keep alive commands as the command-based keep alive command algorithm would. Okay, so that's time-based recovery. Those are the keep alive algorithms that are out there. What kind of time are we talking about here when we're waiting 2 times cat or 3 times cat? And the keep alive timeout time and the command quiesce time, they have to be sized for worst case scenarios. And so you could end up that you could recover much faster. But if you've got the timer going, then you're stuck. You have to wait that amount of time just in case this is the time that the command sticks around in the system. And so the kind of times that we're talking about is if we've got cat going on for 10 seconds and we've got we got the command quiesce time at 15 seconds, then we're talking about 35 seconds before you can start to recover a command. So that means that if you're dropping a connection and there's outstanding commands on that connection, you're waiting half a minute. And these are pretty conservative times. I mean, this is a pretty fast failover for a complicated array. And if you do traffic-based keep alive, which tends to be a little bit more robust because you continue to have the connection going as long as you have traffic, you're waiting even longer. And this is just too long. Now, one of the things to note here is that there are some systems out here that don't put any delay in their retry. We're not very happy with those systems right now. We can reproduce corruptions in our lab very easily with such systems. There are some systems that put just some delay in. Maybe they don't use this calculation, but they put some delay in. Maybe it's a 10-second delay. That is helpful. And so those systems are actually working better right now. But now we've specified this is the time theoretically that you should be waiting. And it's not pleasant. So let's make it faster. These are a few mechanisms that we're going to talk about. The reconnect, we're trying to just connect on the same path with the same controller. We just think that there was a hiccup in the network. The lost host communication, that allows us to find out from the controller through another path that the host, that the controller thinks that there's a loss of communication. And cross-controller reset allows us to reset along another path and find out exactly when the commands are done processing. Now, while all of these are going on, these are optimizations. They're important optimizations, but they can fail. And so it's important for the host to keep the timer going in the background for the timer-based recovery, because if they do fail, you don't want to start the time at that point. You want to start it from the beginning. Any time that's spent waiting will help to clear out the system. So reconnect, this is a technical proposal that is currently in progress. It's extremely preliminary, so the only thing I can tell you is that it works on the same ports. And when it's done, you can be sure that none of the commands are being executed anymore. Tried to put some other stuff down. We're going to wait until we work the details out. So lost host communication, this is a notification that comes from the controller to the host over one of the other paths that's available. This is a fabric. We expect for redundancy that you're going to have more than one path between the host and the subsystem. And so we're going to use those other paths so that we can start recovering. There's a number of advantages that happen when we have this available to us. When the host receives this notification, not only does it find out about a loss of communication it may not be aware of, but it can say, okay, I know that that controller is aware of the loss of communication, and that gets rid of 30 of those seconds, or 20 of those seconds in the recovery right there, in time-based recovery, because I already know that the controller knows that there's a loss of communication. And then it also sets us up for cross-controller retry, because it tells the host, this is really a good connection to use in order to run the cross-controller reset. Talk to me. I'll make sure it happens for you. This is also in progress, but we have nailed down a fair amount of the technical details. We expect this to be able to come out in the next while, a bounded period of time. So here's a bounce diagram of what happens with the lost host communication. The controller detects a loss of communication. There needs to be an internal communication between controller 1 and controller 2. Controller 2 needs to know that this is the same host. And so it can tell that it's talking to host the same as controller 1, and then it sends an asynchronous event notification. The host does a get log page, and inside the entry it finds that controller 1 says that it's down, the communication's down. For cross-controller reset, we're now set up to use that. You don't need a loss of host communication notification to use cross-controller reset, but it's not a bad thing. So the host can trigger a controller level reset on one controller through another controller. Both of the controllers need to be connected to the same host. This is important. We do not want an arbitrary host interrupting communication with another host. And so there are checks in place to make sure that that's the case. This cross-controller reset command, that's a new command, it starts a cross-controller reset operation in the background so that that operation, it sticks around even if something happens to the controller in front of it. When that operation finishes, then the host receives an asynchronous event notification, and it gets the result through a log page. Now, we do want to make sure, in addition to making sure that different hosts can't stop operation of other hosts, we also want to make sure that we don't have spurious resets. That if another connection has opened up with the same controller, we want to make sure that that stuff doesn't get shut down also. So with dynamic controllers, we're saying that we shouldn't aggressively reuse the controller ID. That if there is another controller ID that you can pass out, then this one that you're waiting to see if the host wants to clean it up, then you should use a different controller ID. With static, and the reason for that is because with dynamic controllers, you don't expect to get that controller back. And so you don't have a way of telling necessarily that it's finished cleaning up. When you get a new dynamic controller, you're expecting it to be a clean slate. With static controllers, we have some extra information that we've put inside of identify that identifies which time we've connected between the host and the controller, and which time the controller has come ready. So this is like which set of commands is actually running. And so including that information in identified, it's able to be provided with a cross-controller reset command, and then that prevents us from resetting another time that the host is hooked up with the controller. So here's the success case. The host detects a loss of communication. Cross-controller reset command, it issues it to down another path to controller 2. It gets success back. When it gets success back, that does not mean that controller 1 has been completely cleaned up yet. The subsystem requests a CLR on controller 1, and Then we get success back there. Then we let the host know, yep, we're done. Go and get the log page. And when the host reads the log page, it says controller is done. I've got success here. That means that cleanup is done. We're ready to proceed with recovery in the commands that we've been waiting on. So this is success. This is another example of success. This is where controller 1, there's no cleanup to do because controller 1's gone. Or maybe controller 1 is already done with the cleanup. So the host detects a loss of communication. It talks to controller 2. Controller 2 makes an observation that the cleanup's already done or that controller 1 is powered off. And then it sends back a response that marks it as this is success and you can proceed with recovery. You don't need to, and you cannot wait for an asynchronous event notification. So here's an example of failure. The host issues a cross-controller reset command. Controller 2 says, yep, I got it. We'll start working on that. Subsystem requests a controller level reset. Maybe controller 1 gets it, maybe it doesn't. Start processing it, and it says, well, we're expecting that cross-controller reset is going to take less time than timer-based retry, or timer-based recovery. So we're not going to wait as long internally. And so the subsystem says, okay, there's a problem. I don't know what controller 1's doing. I'm not going to continue working on this. We'll let the host know to come and get the status. And so the host gets the asynchronous event notification. It gets the log page. It checks for the record for controller 1, which says that I failed. Now, it can contain some information in there about another controller that the host can use to try cross-controller reset, or maybe that the controller should just retry again. Maybe just not with me. And when it does that, then there's still a possibility that cross-controller reset can succeed just down one of the other paths. The alternative is that if this doesn't work, then you're back to time-based recovery. Okay. So to summarize the things that we've talked about here, we've gone over some problems that we're trying to prevent. We're trying to prevent data loss and data corruption. This is something that I'm not excited about to see on my customer systems, and they get really excited when they see it. It's just not in a good way. And we're also trying to make sure that we don't handle the non-idempotent commands incorrectly. We've introduced a couple of mechanisms on how to recover from that. One of them is time-based retry. It takes a long time, but it works. We've introduced some ways to speed that up. We're hoping that between these mechanisms that don't take a long time and then having the assurance of time-based retry to fall back on, that we can have a robust system that our customers can use and that they can proceed to use NVMe over Fabrics in their installations, and they can sleep well at night. That's what I have for today. Thank you. Any questions?
A question about the communication between two controllers.
Okay.
So, are you assuming that the communication between two controllers is reliable? Is there? During the recovery process or communication loss scenario, the two controllers may have the communication between the two controllers may have a problem too.
Yes.
So the two controllers, maybe they are healthy, or the controller one doesn't respond to host or controller 2, but the controller 1 is still working.
Yes.
But, no one can talk to controller 1. So I wonder how
do we handle that?
Yeah.
Okay. So the question has to do with if we have an internal loss of communication, if controller 1 and controller 2 can't talk anymore, so what does the host do? And so the answer is I explained that, well, we might be able to direct it down another path. Maybe there's another path that they could use to try and do the cross-controller reset. But maybe no one can talk to controller 1 right now. In that case, the host should be running down its time through the Kato and the Kato time, and also the 2 or 3 times cat, and also the command quies time. And when it gets to the end of that time, then controller 1 should be out of the picture at that point. All of the commands that we're executing on controller 1. And so that's time-based recovery. We don't like to fall back to that because it takes a long time. But if we have to, it's there, and it's reliable. Or it better be. Any other questions? Okay, I think we're good. Thank you.